Good morning, everyone. A great pleasure to introduce Mark Gerry. Many of you know Matthew, graduate student in he will tell us about one of his projects out of quite a few. So please.
Thanks. Yeah, thanks to Vera for inviting me to speak and for the introduction. Today, I am going to be talking about, like Vera said, one particular project that is focused on just trying to get some understanding as to what the kind of underlying physical processes are that are giving rise to some phenomena that you can observe when you look at the evolution, like the dynamics of open quantum systems as they evolve towards equilibrium with a thermal bath. What we sometimes see when we have systems that have sets of nearly degenerate eigenstates is that in the approach to equilibrium, there's this distinct kind of dramatic timescale separation whereby over like a longer timescale, the system does reach the kind of expected thermal state as determined by the temperature of the bath it's interacting with. But there's also a much shorter timescale after which the system actually relaxes to a sort of a intermediate state that's very long-lived, that is characterized by populations that are not yet at the levels that you expect to see in that thermal equilibrium state, and also coherences in the energy eigenbases, which, as you expect, die off when you reach thermal equilibrium. All right. So I probably don't need to motivate too much to this audience why coherence is interesting, but there are lots of kind of questions of theoretical and practical interest relating to coherence in quantum systems. In practice, quantum systems are always open and interact with their environments. And the sort of pervasive or like dogmatic view about what interactions with the environments do is that they lead to decoherence. So in other words, right, any coherences that exist just die off as the system interacts with the bath and thermalizes. But there can be cases where interactions with thermal baths actually give rise to coherences, like I showed on the last slide, right? These coherences showing up and persisting over long timescales before eventually dying off. There are other situations that I'm not really going to be focused on today where coherences exist at steady state in non-equilibrium situations. But yeah, right, so there's all these kind of physical systems where coherences might be of interest, open systems, right? There's some kind of biological processes. So there's been studies looking at the photoisomerization of retinol, right, as part of the process of vision in living organisms. There's questions that have been studied as to whether coherence can help with efficiency or performance of quantum thermal machines. And then also in quantum sensing, these kind of long-lived coherences that can show up can help you get better performance out of probes that you're using in thermometry, as an example. Of course, also, right, quantum information processing. We need to know how we can maintain coherences over long periods of time. The focus for today is going to be, like I said, this phenomenon of long-lived coherences, these long-lived intermediate states during thermalization when we have nearly degenerate levels. And I'm basically going to approach that by just looking at a couple minimal models, sort of the most basic models of open quantum systems that we can look at where we see these phenomena occurring. So one of them is going to be just a spin-boson model, simple two-level system where the splitting between the levels is considered very, very small relative to the energy scale set by the temperature of the bath, right? So it's like kind of like a nearly degenerate two-level system. And then also I'm going to look at a somewhat more complicated model, adding a third level, whereby we do have now like a finite, non-negligible energy splitting between a ground state and a pair of excited states, which are themselves nearly degenerate. So separated only by a splitting delta that's small relative to nu. So we will come back to all that. But first, I am just going to kind of bring everybody up to speed very quickly on quantum master equations, which is the approach that we use to model the time evolution of open quantum systems if they're weakly coupled to their environments. And also just go into a little bit another method for characterizing the evolution of the quantum state that you can use if you have an ensemble that's described by quantum master equations, which is this quantum trajectory approach. And then we'll dive into our minimal models. So we'll talk about the spin-boson model as kind of an example of when you have dissipative dynamics operating within a nearly degenerate subspace. And then we'll go to another case where you have jumps over non-negligible energy splittings, but you still have these manifolds with nearly degenerate states within them. So, right. sort of general overview of how we approach modeling open quantum systems. We're going to start by writing down a Hamiltonian for the whole sort of world, right? The system and the environment. And there will be some contribution that's just the system Hamiltonian, describes, gives you the energy eigenstates and the eigenvalues of the system. And then same thing for the bath, but a lot of times that'll be something like infinite continuum of bosonic modes. And then there will be a contribution that acts on the kind of total Hilbert space, which describes the interaction between the two. And it'll be given by like a summation of these tensor products of operators acting on the system in the bath. So in general, we believe in quantum mechanics, right? We say that the whole system plus bath is described by some density operator rho that evolves according to this Hamiltonian, the total Hamiltonian, but it's not practical to track all of the bath degrees of freedom. There's just too much information, right? What we really want to do is write down some equation of motion to give the time evolution of just this object, which is the total density operator, but with the bath degrees of freedom traced out. So the system reduced density operator, which I am writing here as just rho with no subscripts or anything, just for convenience. And we want to write down some equation that's going to give its time evolution. That's going to be a quantum master equation. And it kind of goes without saying, right? When we take this total rho, we trace out the bath degrees of freedom. What we end up with is a reduced density operator that still has trace 1, still a positive operator, right? Has all the properties you expect of a density operator. Whatever quantum master equation we end up writing down should preserve those properties, right? We don't want to time evolve and find out later time t that we can have something like a negative probability, which again sort of seems like it should go without saying, but it's not necessarily completely trivial to get there. The most general form of a quantum master equation that does have these formal properties we need is the Gorini, Kosakovsky, Lindblad, Sudarshan, GKLS, or very often just Lindblad quantum master equation. This is, like the most general form of an equation that will generate a completely positive and trace-preserving map. So it does have those formal properties, and it's usually expressed this way. So again, right, we have the time evolution of just the system reduced density operator. There's a contribution that is just unitary evolution, as given by the system Hamiltonian. But then there's also these additional contributions which are non-unitary, which essentially represent the interaction with the bath. And they involve these L's, these Lindblad operators, which can be things like projectors onto energy eigenstates or jumps between energy eigenstates. So right, this is how you kind of commonly see it written down. There's another way that I think is very useful to write it that's maybe a little bit less mathematically rigorous, but it really gives you some insight as to what you're sort of claiming open quantum system evolution is like if you're using a Lindblad quantum master equation, which is to say, okay, given the system state at some time t, after some increment dt, what does the state look like if we're evolving, right? The state for an ensemble if we're evolving using a master equation like this. And so again, we see this contribution that's sort of quasi-unitary. It's capturing that whatever effects you get from the system Hamiltonian. And then there's all these contributions associated with the Lindblad operators. That's basically saying that over some increment of time dt, with probability gamma dt, some instantaneous process has occurred, like a jump or a projection onto an eigenstate. And so by this kind of reading, these gamma k's, you can understand them to be like rates for like a Poisson process, right? Something that once you're in a state, if there's a transition out of it, the wait time before that transition happens is going to be exponentially distributed according to this rate gamma, right? Why we end up with this effective Hamiltonian in the sort of quasi-unitary part just has to do with normalization, right? So if there's all these different possible jumps that can occur with probability gamma dt, the probability that your state after evolving for a short time is just what you get through that unitary evolution is technically it's not going to be 1. So that's really where we end up with these anti-commutator parts of the equation, right? Factoring in. So right, so what this is really saying is that open quantum system evolution, if you're using Lindblad form quantum master equations, you're sort of implicitly assuming that what we have is unitary evolution, but then punctuated by these randomly timed instantaneous processes, which are like jumps or projections. You can think of them as being like measurement-like, right? Like you'll sometimes hear people talk about this as an interpretation. at the very least like an analogy, right? Like it's saying that at these random moments in time, your bath kind of measures your system. And then these gamma k's, they set the rates for that kind of random process. So, right. So if we are working with that interpretation, then there's this place that you can kind of naturally go, which is to say, okay, what would be kind of a characteristic trajectory for just the time evolution of one instantiation of the quantum system, right? Instead of looking at the time evolution of rho for the ensemble, if we just took one kind of like specific system, an individual, and said, what are we sort of suggesting its time evolution looks like over time? What it looks like is these instantaneous jumps followed by periods of coherent, right, unitary evolution. This is really just kind of a cartoon example of what that might look like. But you can simulate these, right? If you want to simulate a bunch of examples of trajectories that look like this, you can use Monte Carlo methods, right? Just randomly generate wait times between jumps like this and fill in the gaps with the unitary evolution, right? Knowing your system Hamiltonian. And sometimes this approach is referred to as unraveling the master equation, right? Because the idea is that you can take an ensemble of trajectories like this, and averaging them all together, you should get back the solution to the quantum master equation, right? The ensemble reduced density operator as a function of time. So, okay, yeah. It is, I don't want to spend too much time here, but it is going to be relevant to kind of give the quickest sketch ever of how you derive Lindblad form quantum master equations from microscopic principles, right? We know now what the general form should be of the master equation. We start out with the assumption that the whole system plus bath just evolves unitarily. What you're going to end up doing, integrating this equation up to second order in the system bath interaction. And the truncation after second order is really where that assumption of weak system bath coupling comes in. You need to make a few approximations in order to actually get your equation to a point where it's useful. And what you end up with is the Redfield quantum master equation, which is useful, right? It's this time local Markovian quantum master equation. If you want, you can use that, you numerically integrate it to get the state of the system as a function of time. But this equation alone, it's not of GKLS form, right? So for one thing, it does not necessarily have those formal properties we need. If you use this equation, you could, in principle, end up with things like negative probabilities and negative rates, which not everybody is so comfortable with. And then for that reason as well, also, it does not lend itself to this kind of trajectory picture, this interpretation that we have these periods of unitary evolution just punctuated by these instantaneous jumps. But this is the equation. Don't need to focus on necessarily the whole line here in the interaction picture. One thing that's worth pointing out is that it involves this summation over these omegas, which are all of the Bohr frequencies of the system. So in other words, all of the splittings, right? For every pair of energy eigenstates in the system, there's terms in these double summations for the frequencies associated with those. And in the actual term here, there's this factor that's like an oscillating phase factor, whose frequency is given by the difference between omega prime and omega. So, all right, I can go to the next slide. So we want to get to Lindblad form, GKLS form. The most common way of doing that is to just say, okay, all of these terms in the Redfield equation for which omega prime and omega are unequal, they have these oscillating phase factors. Say, okay, once we integrate up, because of the oscillations, those just won't contribute any significant amount. We'll just throw them away. And that turns out to be sufficient to get an equation that's a Lindblad quantum master equation. But what it also does is it basically implicitly there, you're making the assumption that all the dissipative dynamics are doing is leading to jumps between energy eigenstates. And so as a consequence, the evolution of populations and coherences in the energy eigenbases are completely decoupled. Generally, this is where you get that sort of common view that the bath just causes decoherence, right? As soon as those jumps start happening, you're not going to have coherence anymore. And we have population evolution that just looks like kinetic rate equations. There are situations, though, where this choice is not necessarily going to be a good choice. And that's when, again, if you have near degeneracies in the system, there's going to be terms here where omega prime and omega, right, a pair of Bohr frequencies, splittings, that are not exactly the same, are actually going to still be very close. And so the timescales associated with this oscillation, they can start to be long enough that they start to rival the timescales for the dynamics of interest. And in that case, right, throwing them away might be an approximation that really is not a good one, right? You might really change the dynamics in a way that's no longer reflecting what's really going on. So if you can identify clusters of nearly degenerate states in your system, sets of Bohr frequencies that are close together, a much better move can be to throw away only those terms that oscillate quickly and keep the ones for which omega and omega prime are close to each other. And then the further approximation is you just kind of neglect the difference between the two of them when it comes to actually calculating the rate. This is another way that you can get Lindblad form. And it's going to be a better approximation when you have near degeneracies. I'm just going to check the time. Okay, good. So that brings us to the quantum master equation that we used when we started to look at some of our model systems. It was derived actually independently a few different places, all within the last 5-6 years. In some cases, it's been referred to as the unified quantum master equation. So this, like I said, right, it achieves GKLS form, but it does not just completely throw away the couplings between populations and coherences. It keeps those slowly oscillating terms in the Redfield equation, and it can more faithfully kind of represent how coherences and populations affect each other's evolution. So right, when you have near degeneracies, this can be a much better choice than using the fully secular equation. And just to kind of give an example of what it looks like, right, I'll come back to this V model that I introduced early on. Here, we identified this kind of excited manifold, right, states 2 and 3, as being like a cluster of nearly degenerate states. And then we essentially just neglect this splitting delta when it comes to writing down the master equation, right? So when it comes to calculating the rates and figuring out what the Lindblad operators are. So whereas if you use the fully secular equation, you would see a Lindblad operator that's a jump from 1 up to 2. And separately, there would be a jump from state 1 up to state 3. If you use the unified equation, your Lindblad operator just looks like a jump from state 1 up to this coherent superposition of 2 and 3. And that is going to lead to qualitatively different dynamics. So yeah, just to take a moment here and kind of rehash why coherence is important when you have near degeneracies. I think, again, it's kind of useful to come back to this analogy, I guess, to measurement, right? This idea that you could maybe kind of say that it's like your bath is measuring your system at these random moments in time. Suppose you really were measuring and you heard a click, and that signified a jump, right? That signified some change in energy of the bath associated with a change in energy of the system, maybe jumping from the ground state up to somewhere in this excited manifold. If the splitting between 2 and 3 here, delta, was so small that it was smaller than the resolution of whatever measuring device you're using, then you really wouldn't have which way information about whether your system jumped into state 2 or into state 3, right? And so that lack of which way information basically means that, yeah, there's no necessarily reason to assume that coherences need to have died off, right? It's analogous to like the double slit, right? If you can't resolve which slit the particle passed through, you can see an interference pattern on the back wall, right? So there's something similar going on here. All right, so I think that's about as technical as things are going to get. Now I'm ready to actually start talking about the models that we looked at and the phenomena that we were interested in investigating. So yeah, we'll come back to the V later, but even simpler is just this spin boson, this 2-state system, coupled to a, right, that's like a spin coupled to a bosonic reservoir. In this case, the interaction is just characterized by one term, operator on the system Hilbert space and an operator on the Bath Hilbert space, where the system operator, it's actually something somewhat exotic, right? We're used to seeing something like strictly off diagonal or strictly diagonal elements in this system operator. Here we have both. It's worth noting again that with the fully secular equation, you'd see something like jumps between the eigenstates and independently decoherence, right? Measurement of which state you're in. But because we really want to neglect this splitting and we want to assume that when it comes to deriving the master equation, right, we don't necessarily take into consideration energy scales as small as the splitting delta, what you end up with is actually a master equation that only has one Lindblad operator that is just proportional to this system operator S. And then there's a rate that's proportional to T multiplied by the A, which is like a dimensionless coupling parameter between the system and the bath. So what this is actually kind of saying, it's sort of odd. It's saying that this instantaneous process that happens at these random moments in time is sort of like applying a Hadamard gate to the system, right? So you might think it's a little bit unintuitive. But nonetheless, right, we can go ahead and just find the solutions to the master equation. So supposing that we start in the ground state, this brings us back to those plots that I showed on the title slide. We have a method for analytically finding the solution by just writing down the Liouvillean for the system and then just getting the eigenvalues to leading order in delta. So actually only including delta order contributions if the eigenvalue is otherwise 0. And yeah, what we see is, right, there's this short time scale that shows up over which the system goes to this long-lived intermediate state where the populations are at like an intermediate level. And then there are coherences between the two eigenstates. And then over this much longer time scale, tau 1, the system actually finally goes to a thermal state, which again, neglecting order delta contributions is actually just the maximally mixed state, right? Equal populations in these two nearly degenerate levels. So these are the forms of the lifetimes that show up in our analytic solutions, right? Tau 1 is set just by the rate for the dissipative dynamics, right? That rate that determines the time scale for the wait times between these instantaneous jumps. But tau 1, this longer time scale, goes as gamma over delta squared. So it depends on the splitting in this sort of unusual way that to us was not immediately kind of clear where that came from. So we wanted to understand a little bit more where that came from. The first thing that we did was realize that the Lindblad operator is diagonalizable. And we just kind of said, okay, what do the dynamics, look like in this basis where the Lindblad operator is diagonal? So we identified that basis. Just going to call the states psi plus, psi minus, doesn't really matter what they are. In that case, Lindblad operator, it looks kind of like a poly Z, right? So what it's going to do is add a relative phase of pi every time it kind of smacks the system, right? And that's really nice because when you have a diagonal Lindblad operator, what you can do is you can go with this interpretation that the system-bath interaction does just lead to pure decoherence. So in other words, the system is just, or sorry, the bath, if you want to use the analogy, is kind of measuring some property of the system. It's just that it's not decoherence into the energy eigenbasis. So it's measuring some property, not the energy. And that means that it leads the state to collapse to one of these basis states that's not an energy eigenstate. And after that collapse occurs, there can still be coherent oscillations, right? In this basis, in the system Hamiltonian, there's going to be like tunneling terms. The nice thing that we saw in this basis is that the two timescales, the long one, tau 1, and the short one, tau 2, were separated between the different elements of the density operator, density matrix, right? So now the populations really stay fairly steady over a much longer time scale until after around tau 1, they do decay to 50-50, right? The expected maximally mixed state. And it's only over this much shorter time scale that coherences in this plus minus basis decay to 0. So right away, you can start to understand why maybe this shorter time scale, tau 2, is just 1 over gamma, right? It's just the dissipative dynamics leading to the dying off of those coherences. But we still really wanted to understand where this came from. And again, to me, it's still not totally clear, right? Okay. So the next step to try and just get some more intuition was to look at some trajectories. As I kind of introduced a few slides ago, right? If we can look at, given the master equation, what you're kind of supposing one kind of characteristic individual system might be doing as it evolves in time. And what you see is here plotting just over a time interval that's actually on the order of 1 over delta. So, right, so now we're in a basis where there can be Rabi oscillations. This would be like the period, or like on the order of the period of what those Rabi oscillations would be. The population really doesn't change very much. It's not constant. It kind of evolves according to this jagged curve, but it stays pretty steady, pretty close to its initial value. It's only, again, over this much longer timescale tau 1, that correlations to the initial value really do die off. And it seems like the population can be anything, right? They'll average out to 50-50, as you expect in the thermal state. The off diagonals, which I am hesitant to call coherences because we're not talking about the ensemble here. We're just talking about one exemplary system. They are constantly flipping sign right away. And the wait times between these flips are characterized by that tau2, right, as we expect. So tau2, it's so short here, even relative to 1 over delta, that it's barely shows up, right? I'm marking it there, but it's just very close to the vertical axis of the plot there. And so you can see by looking at this why over a really short time scale, an ensemble of trajectories like this would average out to 0. But also, all of these sign flips are happening inside this nice, like, sort of sinusoidal envelope, which is a hint as to what's going on in the system, right? It's a hint as to the fact that there are these coherent Rabi oscillations that are happening in this new basis that we're studying the evolution in. But why is the timescale for this dying off of the coherences, or sorry, the population, the correlations to the initial population, so long, right? It can happen. And it turns out that it has to do with fluctuations in the amount of time between jumps, building up to the point where you lose eventually, over a much longer time scale, you lose correlations to that initial value. So because we have coherent oscillations and these like dissipative jumps happening simultaneously, we found that the block sphere was kind of a useful tool for visualizing the evolution. And again, right, the simultaneous kind of occurrence of these two processes means that there's two processes that show up kind of geometrically on the block sphere, right? The unitary contribution is what you might be familiar with from quantum optics, just precession around like a drive vector, which encodes the parameters of the system Hamiltonian, right, the Rabi oscillations. But then we have to add to that these jumps that occur at random times according to this rate gamma, which again, add pi to the relative phase, so essentially flip the state across the z-axis on the block sphere, right? So if we want to see what the evolution looks like for, again, one of these characteristic trajectories, okay, supposing we start in the ground state, here, the state is the green vector there. It's going to be anti-parallel to the drive vector, which makes sense. The ground state of the Hamiltonian is a stationary state. But after a short time, on the order 1 over gamma, you're going to see a jump, which is going to reflect the state across the z-axis. And suddenly now these coherent oscillations can begin. So when they do, that's going to correspond to the, I guess, the green vector here is going to move out of the xz plane into the negative y territory. And there's going to be changes to both the relative phase and the population. So in this case, you would actually see, as these oscillations begin, the population of this psi minus state growing a little bit. But the thing is, after not very long, another one of these flips is going to occur. And when it does, the population evolution is going to start going back in the other direction of the direction it was just going. So right up to this frequent flipping, we have these small changes that are occurring to the populations, but aren't having very much time to accumulate before another flip happens and those changes get undone. And so the population ends up kind of getting pinned close to its initial value for a much longer, where am I? There I am, period of time. The off diagonal, on the other hand, right, the relative phase, it actually does have an opportunity to kind of trace out these clean circles around latitude lines, just up to a kind of a constant flipping back and forth across the z-axis. So that's where you get that sinusoidal envelope. Right, and just kind of one more thing about this picture. Those the wait times between jumps, they do fluctuate, which means that eventually you can have a loss of correlations to the initial value of the populations, and it's going to be over the time scale over which those differences, those fluctuations in the wait time, kind of build up to the point that eventually this vector is able to kind of make its way up the block sphere to the point where it no longer really remembers where it started. So I do have a little movie. Maybe I won't show all of it, but is this going to work? Maybe over here. I kind of described everything already. Damn, I don't know if this is going to work in this. It was working on my laptop. That's too bad. I mean, I described everything already. You were just going to kind of see this green state vector start relatively pinned at just about at the same latitude on the sphere, but very gradually kind of make its way up to the equator until you reach that point where those correlations die off. So all right, so that was kind of one picture, that spin-boson model, where we really looked at what the master equation was sort of suggesting the dissipative dynamics look like. And from there, we were able to kind of come up with this story as to why this really long timescale emerges in the decay of coherences of the population. Another sort of story that's very similar in spirit, but actually distinct in a few key ways, is looking at the V model. So this is a situation where now we do have a finite splitting from the ground state up to the excited state, or the pair of excited states. And so that actually means that there is like a distinct change in energy of the system, and there should be an associated change in energy of the bath. So in my opinion, this is like kind of a clearer interpretation as to what's going on, right? The bath can excite jumps in the system's energy. And crucially, the expectation value of the system Hamiltonian will not be constant as we evolve towards thermal equilibrium, right? If you start in the ground state, that final thermal state is going to have a different expectation of the system Hamiltonian. So the interpretation that there's some basis in which the dissipative dynamics just cause periodic coherence won't work. And in fact, there are two distinct Lindblad operators here that are not simultaneously diagonalizable. One is a jump up to the excited states, right? It's actually a coherent superposition of 2 and 3. And then the other one is a jump down. And the associated rates need to stand in a detailed balance relation to one another to ensure that you get that thermal state at equilibrium. So you can tell a very similar story here, right? Get the solutions to the master equation. And once again, we do see this intermediate state where the populations are at intermediate levels and coherences have built up in the energy eigenbasis before dying off. And in this case, right, again, we see very similar timescales, right? This longer tau1, which again depends on the splitting delta, this small splitting in this way that wasn't necessarily super clear. And then shorter tau2, which is only determined by the rate for the dissipative dynamics. We also see these prefactors here, which can be expressed in terms of these partition functions, right? So Z, it's the partition function for the system. Up to leading order in delta, right, neglecting contributions of order delta. And then we also saw showing up time and again this Zi, we called it, which is also a partition function, assuming you only had a 2-level system. So assuming basically only one of these two states were here. And you just had, right, that would characterize your thermal state if you were just talking about 2 levels separated by some splitting nu. So that was kind of a hint as to where to go with this story. So what we did was, again, we found a basis that was more kind of natural for describing the dissipative dynamics. In this case, it did involve just taking the plus and minus superpositions of the two excited states. And then the Lindblad operators become very simple. So what we're basically saying is, right, at random moments in time, the bath either causes the system to jump up to this plus superposition or jump back down to 1. Crucially, the minus state is not involved in the dissipative dynamics, right? So there's only a jump now from 1 up to plus, and relative, like with respect to the dissipative dynamics, this minus state is basically dark. However, we're not in the energy eigenbasis, so there is now a coherent coupling between plus and minus. So population can reach the minus state only once we've jumped up to the plus state, and then enough time has passed for these coherent oscillations to actually put population in that minus state. And so changing to this basis, it did show that, in fact, yeah, there's this minus state, which is like the dark excited state, which only shows population building up over this much longer timescale, tau1. What's happening over the shorter timescale, tau2, is these populations of the ground state and plus, they're reaching the levels that you would see if you just had a 2-level system that was thermalized, right? So the dissipative dynamics only really sees 1 and plus, and it's causing that population exchange to reach the levels where you would have like a 2-level system, or a thermal state for a 2-level system, right? And it's only over this much longer time scale that eventually the whole system is able to get some population into minus as well, and you have the proper Boltzmann distributed right thermal state. So yeah, just as a kind of a little demonstration, we looked at some trajectories here as well. And it is just kind of a reiteration of what we're saying. The quantum master equation is suggesting the evolution of like a single system would look like, right? So it's maybe a little hard to see, but we see these jumps up to the excited state. So that's when the population of state plus, the orange line here, goes to 1. And then once it does, those coherent oscillations that put some population into the minus superposition can begin. But before very long, right, you expect to see a jump back down, and that kind of resets everything. So again, right, these populations, that population of that minus state kind of gets pinned to 0 over a much longer time scale until you reach a point where enough of these trajectories, right, the fluctuations in the wait times between these jumps allow for enough of these trajectories to have some population in that minus state too. And the coherences have really died. This is just kind of taking 100 of these sort of simulated trajectories and averaging over them, just to show that you do kind of start to get back, although it's noisy here, only using 100, the solutions to the ensemble, right, quantum master equation that you would also get if you just solve the quantum master equation, right? So that sort of concludes, right, the stories that I have to tell. We really, the project was about understanding, right? We wanted to get some understanding as to what underlying process is. We're giving rise to this phenomenon where we have these long-lived metastable states that often show coherences that build up as a system thermalizes. And the way to kind of capture those effects was to use a quantum master equation that takes into account the interplay between population and coherence evolution. And then, yeah, the approach that we generally took was to look at the dynamics in a basis that was in some way more natural for expressing what the Lindblad operators are saying the system does. And we understood these phenomena as being a result generally of dissipative dynamics and coherent oscillations occurring simultaneously, right? And so that was able to kind of shed light on where these timescales came from that we already kind of knew were in our solutions to the master equations. So I'll thank Devira, and I will also thank Michael Q. Ming, who visited us a little while back and introduced us to all this trajectory stuff and some thermodynamical problems that he was beginning to work on, right, through this, I guess, lens. And yeah, I'll conclude there. So thanks for listening.
Very, very nice. Yeah, I enjoyed it. Listening to your talk. Questions, please?
I have two questions. First one would be, so you speak about this measurement interpretation of interacting with a buff. And then I imagine this experiment where, okay, you say that delta is very small, so you don't have a resolution to distinguish between the two excited states.
Yeah.
Do you think that we might do an analogy with something like a weak measurement, in the sense that like we don't have the full information of what is the excited state? And do you think that we could make this analogy, or there would be some problem with that?
So, right. So this trajectory sort of approach, it has been kicking around for a long time in like quantum optics, where it was applied to situations where you were literally making a measurement and you had something like a time series of detector clicks that you could then kind of go back and reconstruct the actual evolution of like one trajectory just by kind of filling in the gaps with coherent evolution between these clicks. In the case of open quantum systems, I think that it is probably more correct to think of the interaction with the bath as being a weak measurement, right? So in other words, the coherence dies off, especially if you have something like a pure decoherence model, right? The coherence dies off, but we don't know what the state of the system is after. And that's why we're using a quantum master equation, right? So it's several slides ago. But when I kind of showed this, what I said was like a somewhat more intuitive way of writing the quantum master equation, right? You can really think of this term as like mixing in with probability gamma dt that a jump has occurred, right? So what you end up with is with this mixed state that kind of takes into consideration all these different contributions from the different possibilities as to what jump may have occurred or not, right? I do think, yeah. It's, yeah.
Okay, and the second question, okay, I don't really. So the question is basically that I don't understand this idea of there are those. We go to this for the V model. We go to this basis where the two excited states are on the same energy height, let's say,
Yes.
and then it's the time where we evolve between 0 and plus, and the minus is kind of hidden. This is when we have the most coherences. I kind of don't have intuition for that. Like, why the time where we, because I guess that it's the unitary evolution that gives us the mixing between plus and minus.
Mhm.
So why the maximal coherences are when this happens?
I think kind of the simplest way to answer that is to just say that the jump is only up into the state plus, right? So that this plus superposition corresponds to a particular choice of what the relative phase is between right the two excited states. So every time a jump happens, you always end up in that same state, right? So you never, if you had other Lindblad operators that were jumps between 1 and minus, you would not see this effect, right? It would be equivalent to jumps to 2 and jumps to 3. It's just the fact that the dissipative evolution kind of favors jumps into one particular coherent superposition with one particular right value for that relative phase between the two states. Yeah.
What was the coherence in the plus minus basis? That's the different basis. The two, three in the original basis, they were going that's fine.
Yeah, so I was careful to say that the populations are as though a two-state system has thermalized. It isn't that simple, right? The coherences do show up in the plus minus basis too. And they evolve. They right for an individual instantiation of the system, they're going to oscillate coherently, right? So again, we have coherent oscillations between states plus and minus. So at least for a single trajectory, you would see right, those coherences build up and then decay and then build up, right, sinusoidally over time. So yeah, I think they don't die off right away. If you were just to numerically solve like the master equation, you would also see coherences build up in that basis too, I'm pretty sure, before everything dies off as you go to thermal equilibrium, yeah.
Right, you showed the plot of your single trajectory of the coherences with that nice sinusoidal envelope, I think was it the spin-boson model?
Mhm.
If you do like the classic Monte Carlo thing where you create a bunch of trajectories and then average them all, do you still have that sinusoidal envelope with the average? Because it seems like it could just average it to 0 if you have a bunch of those.
It definitely does just average to 0, right? Because these sign flips that are constantly happening are happening on every time to the beat of their own drum, right? There's no correlations between different trajectories with respect to that. And so that's what, right, if you average over many kind of exemplary cases of this, you should absolutely get back this, right? Just the decay to 0 over that shorter time scale tau 2.
Right, I'm going to ask another question about what you just said. You said exemplary cases. Do you have particular criteria to determine if something's a good trajectory versus a bad trajectory?
Oh, that's a good question. So we used, and I should have actually mentioned this when I was presenting, we use Q-tip to generate these, and there's like a built-in function, photocurrent MESolve, where you just plug in your Hamiltonian and your jump operators, like your Lindblad operators, and it just gives you trajectories. In this case, there was no post-selection that happened after that. Off the top of my head, I can't think of a situation where there would be, right? Like it's pretty, what these trajectories are going to look like qualitatively is pretty well determined by the master equation that you're working with. Yeah. Exemplary, yeah. Characteristic, yeah. Examples. I just meant like they were examples. Yeah.
So this quantum trajectory approach, is this generalizable to cases where the coupling is stronger, where you can't work with master equations?
Yeah, great question. That classic question. So I would say like my gut instinct answer is like this trajectory approach as we're using it here, the answer is no. And in fact, you can't even use it, or at least there's no straightforward way to use it, even if the coupling is weak, but you just want to use the full Redfield equation. Because right, even here, if you kind of look a little closer at the details of the Redfield equation, we have this S beta omega, and then S dagger has different subscripts, alpha omega prime, right? We really lose that interpretation that the dissipative dynamics are like the state being projected onto some particular eigenstate or something like that. And so already right away, like there's no clear way to build a characteristic trajectory. There has been work done to try and, for certain strong coupling problems, reframe them as problems to which you can still apply quantum master equations, right? This reaction coordinate effective Hamiltonian method that like, some members of our group have been working a lot on. So in that case, you get to a point where you can use a master equation again, and then anything like this would be totally fair game, yeah.
But when you talk about like this kind of problem for you or
I would say kind of most generally, I'm just talking about every contribution to the dynamics that comes from this part of the master equation. So basically everything that's going on that isn't unitary evolution. And so, yeah, so then right, this interpretation that comes from quantum master equations is that you might think that that looks like these instantaneous jumps that occur at random moments in time, right? That those are the dissipative processes, yeah, as I've been saying, yeah.
Well, thank you again. Indeed, I wanted to, you highlighted my QME. Goes back to the point I was trying to make last week and I was like every week. And Michael gave a seminar, was it 2 years ago, 3 years ago? He came to see me, he gave a seminar.
2 years ago.
Yeah, and that actually started this discussion. So with that, again, I want to encourage you to, think about people you want to invite, approach your supervisor, or bring them here. We stay a couple of days. There are discussions and new projects. So yeah, with that, thank you very much, Matthew, for a very nice presentation.
Thanks a lot.